Welcome to the February 2025 GoldSim webinar. Today we'll be talking about simulating stochastic daily min and max temperatures, and I'll be walking through the formulation of the model, how it works, and then demonstrating how you can implement it. So this model was developed by some folks at the U.S. Department of Agriculture, Agricultural Research Service, actually, in the 80s. And it was developed in Fortran. It's called WGEN, WGEN. And we have it on our library. You can look it up. It's implemented in GoldSim. But I have broken it out into only the precipitation part and the temperature part. And today we're talking about the temperature part. The reason I broke them out is because the precipitation, well, you can watch one of our previous webinar I did on this, describing a change that I that I made to that model to help simulate longer term, multi-year, multiple decade even simulations where you could have long-term, for example, long-term droughts. That was something that was not very easy to simulate using WGEN, so I broke that out and developed that, and you can watch that webinar recording if you'd like, or let me know if you have any questions about it. But today I'll be talking about the temperature portion of it. So this part was also extracted from that original model, and I fine-tuned it a little bit just to make it more GoldSim centric. The calculations are the result is the same. It's just some of the things are done a little bit differently between Fortran and GoldSim, but the result is the same. So and basically the algorithms are the same. And yeah, somebody asked if about the archive, the recordings of the webinars. Yes, so I do always post the recordings of these webinars on our website, and I can point you to that at the end. Okay, so what we're looking at right here is the result of the temperature. I'm calling it TempGen because it's the temperature part of it. The result of running TempGen for a specific location where I had some temperature data that I was able to build the model from. And this is showing min and max and also average daily temperatures for a given year. And you can see that the values are bouncing around, but there's also a dashed line showing a smooth curve. That's an important component of it, which I'll describe here in a second. But this is what the result would look like. You'd have these three outputs mainly: the min day, or the min the minimum daily in blue here, maximum daily in red, and then you can just average the two. So these can become a useful driver input parameter for environmental systems type models that you might be working on. So let me just back up a little bit and talk about how this is all implemented. So what I'm going to do is I'm going to go to a different model that's called TempGen parameter generator, and similarly, well, actually exactly the same as what's done in WGEN, is a set of algorithms that allow us to develop just a pretty small set of input parameters that can drive the entire temperature model. So when I run this model, I end up with this table right here. So these are all of the inputs that you need for this temperature generator model. So it tells us and these it says K here. These are values in Kelvin. This is all the calculations are done in Kelvin because when you're dealing with increments of temperature, you have to use a different kind of unit, and there's more room for making some mistakes, and so just going strictly with Kelvin works. But you can always just have GoldSim convert these to Celsius or Fahrenheit at any time. So we have to differentiate between a wet day and a dry day. So it calculates the maximum average maximum daily temperatures when it's wet versus when it's dry. Dry is this first number, wet is the next one, and then we have amplitude, and we have average minimum temperature, which is not significantly impacted by wet versus dry. So there's just one of those numbers, and then we have coefficient of variation and some other factors here that are used to drive the seasonal changes and the seasonal changes through the year, which I'll get into here in a bit. But first, let's talk about how we generate those parameters. So the first thing we need to do is we need to find a data set. And where I went to get the data is here. So depending on where you are, there's different places you can get data, but I got mine from here. I can get precip and temperature data, long-term historical data sets from here. So that's where I got this information for precip and min and max daily temperatures. And if I open up one of these, this is for a location in Logan, Utah in the US. And when I click on the data here, you can see I've got quite a bit from year 1900 daily, by the way, all the way down here to 2024. So quite a bit of data that I've got in here. And one thing that I just can't stress enough here is that you really need to make sure that you're not missing values, because in GoldSim, you have a 1 day, in this case, we have a 1 day time step, and it's going to march through every single day and look at the values. So you can set up a time series to interpolate, and that's exactly what this time series will do. And so maybe that's fine for missing a few days here and there, not a big deal. But just keep in mind that there are a lot of data sets out there that are missing, more than a month of data easily, or years maybe. So just, obviously we need to make sure that that's all cleaned up first before putting that would definitely impact the way that the model is operating, obviously. Also, we do need to have precipitation that's aligned with the same temperature records here, same time frame and everything. The reason we need that is because that does impact our maximum temperatures, maximum daily temperatures. So those are the three inputs really that you need, just those three. And then what the model does, I'm just going to zoom down inside the model where most of everything's happening. That's right here, where we do a excuse me, we do a Fourier transform analysis on the data to develop a smooth curve. And there's a drawing here. This is not temperature data that this is being done on here, but I just grabbed this from the internet. But it's a similar process where it takes kind of noisy data and then it develops a smooth underlying curve. It represents the underlying seasonal changes or longer term changes over time. And so that's essentially what we're doing. And so again, these calculations were all converted from the Fortran code. So you run the model on the historical data, and then we come up with these with these coefficients. And so we do that for dry days and also for wet days. And so these are done in two different containers, but they're the same calculations, just for the different whether it's wet or dry. And then if you come up a little bit further, then you see that they're just copies. We do the same exact thing for the daily minimum temperatures as well. I'm happy to answer any questions that you might have about this, but essentially you just run the model for the duration. If I go up here to the simulation settings, then you see that the duration here is the duration of the data in the time series. I can't remember exactly why I went to 2018 instead of 2024. I think I may have updated the data set, so I probably could actually run this all the way to 2024. Let me just see if it should allow. Oh, unless maybe the precip didn't go that far. Let me just see here. Okay, no, it does. One thing that with these models that you want to be a little bit careful of is just it's a good idea just to start it, just to run it for a whole entire year, starting in January, because we're doing calculations that are looking at seasonality, and so you just want to capture a whole month and not start in a strange time of the year. Let me bring this up to 2024, see if it still runs, and you can see it's pretty fast. Okay, so these numbers probably changed just a little bit. Not that big of a deal, but anyway. So what you do is essentially just take these outputs, and this is a one-time thing. You just run this one time, and now you have your set of inputs that you can then use to generate stochastic daily temperatures for any duration, for any time frame, in any of your modeling that you're doing for that location. So we would just copy these and then go over to the model, which is over here. So this is the TempGen model, and then you would just come in here and go to the parameters, and then the inputs are separated into two different input tables. The first one has the units of Kelvin, so you'd paste those in here, and then the other input is the unitless input parameters, and put those there. There is one other very important input in the TempGen model, and that is this input here called cool start day. So this is the day of the year in which temperatures are at their warmest and start to cool down, and it's really just setting the phase of our oscillating seasonal average temperatures, because what we do is we use using the Fourier transform that I was mentioning before to essentially define that smooth curve, and it's all being done here in a script where we use the cosine and that cool start day to determine where the wave peaks and then drops back down. So in this case, in the northern hemisphere, then we peak in July. If you're in the southern hemisphere, then you would change the cool start day to probably something, I think around day 20, I think, of the year, I think is what it is. And so that's one thing you would have to change if you're on the other side of the world. Okay, so that is the main driver, and then it goes through and adds in some of the other coefficients that we've put in to provide this main output, which is the kind of the smooth seasonal trend. Okay, so you can see here we're running a future period, and we've got just kind of the smooth curve of the maximum and of the minimum. So like I said, you can run this for any period. Let me just do that real quick and make sure it's not running Monte Carlo. Okay, so I could run this for multiple years. I just change this to run until 2031, and it runs just fine. And you can see that it's now just repeating the same cycles over time. Now, I will say, and this question came up earlier in my last session, that these numbers are constants. These average temperature numbers, these are constants, but you could make these not be constants. You could derive them in another way outside of this container. So for example, if you wanted to simulate a long-term trend or some sort of maybe randomness in this number going forward, then you could certainly just replace this number with an output that that does that kind of thing. So in the case of, for example, simulating climate change into the future, then this model could provide you a way to more easily implement trends like that, but still maintaining the overall seasonal variability. Okay, so we use the result of the algorithm that I mentioned in the parameter generator. That's done one time, and that's what sets this seasonal trend. But we still have the ability to adjust the parameters that are driving that, and that gives us that smooth curve. But on top of that, we want to implement some uncertainty and some randomness on a day-to-day basis. And so the way that that's done is with this stochastic element here. It's just a normal distribution. It does have a truncation on it. This is also carried over from the original WGEN model. So when I open this, you will see it's truncated here, but it's for the most part a normal, similar to a normal distribution, just doesn't have the tails going out. But it's just a normalized what am I trying to say? It's a normalized distribution, and it's centered at 0. So it has a standard deviation of 1. And so what we're doing is every day we sample a value from here where the mean is 0. And then we use another script element to use a method that's an autoregressive moving average. And so what that does is we start with two matrices, matrix A and matrix B, and these contain coefficients. They're just three columns, 3 rows, and this is done with a matrix constructor. You don't have to do it this way. We could have defined this matrix in a data element out here just as easily. But for those of you that haven't used vector and matrix constructors in GoldSim, just know that in any kind of equation in GoldSim, there are built-in functions that you can, if you just right-click here, functions, and then we have a whole bunch of different kinds of built-in functions, and the last set here, array operators, contains in here the matrix constructor. So really, it's just a way to kind of on the fly in your equation develop a matrix. But these numbers were derived by evaluating many records of temperature values from multiple locations around the U.S. and over many years, and so it's essentially calibrated from that. And there was also a study done since then where they found that these numbers can also be applied globally. And if you're interested, I can point you to those references. Okay, so the first matrix A, that essentially applies persistence to the randomness. So what I mean by that is that it allows us to provide uncertainty to the daily values, but it's based on the previously sampled values. So it's kind of like a way to have some memory in the system. So if it was really hot yesterday, then today it will probably also be warmer or hot. as well. And so the matrix A coefficients are being applied to an extent to a value that was calculated from the day before in the simulation. It's a way to kind of infuse persistence into the model to look at the previous state. And you can see it in the equation down here below. So down in the equations down here, where we're calculating ultimately the randomness for the day, there's these two variables, R and double R. Double R implements this matrix A, and you can see it's multiplying it by this variable called result. And those of you that are new to a script element in GoldSim, whenever you refer to tilde result like this, you are referring to the output of this script from the previous update. So it's previous value multiplied by the whatever index we're looking at of the matrix as we go through this for loop. And this is all repeated every time step. Okay, and then B, what B does is it's providing the random variation, the scaling on top of all of that. So it takes the random number from our stochastic, this is E, and you can see that's here, and it's multiplying that, or amplifying it by these coefficients. They're not all positive numbers, by the way, as you can see here. So they're going both positive and negative there. Then we just add the two together here to come up with the result. And so I would say it's kind of like, to describe it generally, it's a sophisticated way to generate randomness going forward in time that also applies some persistence to the randomness from previous time steps. And that's how, and you could say it's kind of like applying an autocorrelation. When you're using a stochastic element, you're autocorrelating it somewhat to its previous values. Okay, so we have randomness on a daily basis generated here, and then we have our seasonal smooth seasonal trend here. And then we're just combining those two features to then come up with an overall daily temperature that follows the seasonality, but also has the randomness from day to day, which is seen here. If I zoom in, then you can see the combination of the two things there. And so looking at this, you can see how the values aren't just jumping up and down randomly, right, every day. You can see that there is kind of a buildup sometimes where it's running higher than the average, and then it starts dropping down and stays down sometimes, drops down lower and stays down. And that kind of that the way the patterns here are supposed to mimic historically what we see in the historical time series. And if you go to our website, let me go here. So go to the GoldSim Help Center, and by the way, that's support.goldsim.com. So if you go there, then go to the model library here, and then under hydrology is where you will see this precip-gen. You have to go to the next page, and sorry, not precip, TempGen right here. In this article, so I walk through basically what I've been describing, how everything works. But then if you scroll down to the bottom, I've also included some testing results. So I ran the model for a particular location, and then I compared it to the historical. And so you can see these charts that show these comparisons both on an average basis. So in this case, I'm looking at just taking the averages for the periods, the monthly periods, and by the way, it shows a year here, 2025, 2026. You just ignore the year. This model has been run for 123 realizations. So that means I went to the historical record and I said, okay, I want you to sample, calculate or sample the historical record all the way from 1900 all the way forward to 2023. And then I want you to also simulate a similar period, just a TempGen simulation, and then compare the two. And then I did the same thing on a daily basis. And then I took the percentiles. So if you run all of the years on record and then you say, okay, what's the 98th percentile of those? Well, that's going to be this red line up here on the top. That's the 98th percentile of the historical record. And then our simulated is the blue right below that. So you can see that it's fairly close to that. So I highly recommend that you do something similar to this when you run the model for your location. It's a very easy thing to do, to just essentially just run your model, but then also compare it to the historical period. And that can easily be done in your model by doing time shifting. So let me just show you that really quick. So if you're running this model, and if you have your historical data set, just bring your historical time series into your TempGen model. And in the time series, go down here to the more, and then check this box to enable time shifting. And what this will do is it will allow you to, you could either, this would be fine just right here if you only had one time series, but since we have multiple time series that we'll be comparing, we want to shift the data years in the same way. So you could say, starting with year 1900, I want you to, essentially you would do something like this, year 1900 plus realization minus 1. And so what this does is it says on realization 1, we're going to go grab the data from 1900. And then on realization 2, we're going to grab the data from 1901. And then it just continues and sequentially walks through all that data. And that's a good way to compare your time series record with your simulated outputs. And so that's what I did to generate those comparison results. I'm happy to walk you through that, to actually implement that if you're wondering. And I can show you that if you'd like. Somebody asked, is there a correlation between daily min and daily max temperature? Yeah, there is, and if you go to the other model over here, then yeah, you can see that. And I didn't actually plot that correlation, but it would be interesting to see that if you took the historical record and plotted the correlation. That's not something I have done yet, actually, but that is definitely what we're seeing in the model. I would imagine we would see something similar, but I mean, I'm sure there could be a lot of days where you have an extreme max and an extreme min on the same day and the same 24-hour period, but probably most likely it's going to be somewhat correlated on a day-to-day basis. I hope that answers your question, but that is definitely the case in the model itself here. As you can see, the blue and the red line, they're both trending in the same directions on a daily basis. Okay. The other thing that you'll notice here is that I have the PrecipGen model in here. So I was just talking about the TempGen model, but it is a function also of rain. So the TempGen model right here does have this input. It needs to have the input of precip because, like I was mentioning before, the temperatures especially the maximum daily temperatures, are impacted by whether or not it's been raining or not. So because this is a simulation, simulating random daily temperatures, I need to also have random precipitation. However, the two need to be coupled. They're coupled together. They can't just be totally independent of each other, right? So that's why the temperature output then has this influence toward the temperature. So in reality, what we're doing in this model is we're simulating random precipitation, but this is based on historical data as well, by the way. So, and this is a whole different topic, but you can't, like I said, I did recently give a presentation on this one, and you can look that up and watch that webinar as well. But the output of PrecipGen does drive the temperature outputs right there. So this is essentially the functionality. And so the way that it's built is to essentially just copy and paste it into your model, and then it would be ready to use. But you do have to go through that initial step of putting in your time series of measured data and generate the input parameters. But once that's done, that's just a one-time thing. Then you have this model ready to go for as many simulations as you need to do. Let me just mention how to get the models themselves. So if you go to this page, temperature simulator, and then scroll all the way down to the very bottom, then down here, you'll see here's the TempGen model, and here is the parameter generator. So those are the two that you're going to need. You first run the parameter generator, then you get the inputs, and then you can just copy and paste TempGen into your whatever model you're using, and then you won't need the parameter generator anymore. That's just a one-time thing, right? I've also included the test model that I showed the results of earlier in this article, and you're welcome to get that. It's essentially these two files with the data set, so you can reproduce what I did, but you could also use the same logic to test your data for your site. So what kind of things can we do with this model? Let me show you a model where I've implemented this temperature model. So here's a model where we're simulating a reservoir, and we want to simulate the water that flows into this reservoir, which is driven by rainfall that falls on a watershed and then flows into the pond. And we also have evaporation occurring, but the rainfall runoff process is impacted significantly also by temperature as well. We also deliver water from this reservoir to service irrigation supplies, and those are also driven by temperature. So this model is a good use case of implementing a temperature generator that has impacts in multiple places throughout the model. And this would be the case for a lot of system models where you're modeling something that is out in the environment, obviously. So that's why I thought it'd be a good idea to show you some ways that it could impact your model. So here I have, once again, PrecipGen, TempGen. I just copied and pasted these in here. And then what we're doing is, in this model, we're simulating snow accumulation and snow melt in a watershed from that point, we then also have the snow melt and also rainfall on a watershed, which generates runoff. That we also have losses from the watershed due to evapotranspiration, also some seepage, but evapotranspiration, we can capture that by simulating evapotranspiration that's driven by temperature. The evapotranspiration also obviously drives, in this case, water demand for irrigating crops. So we can have an influence there. And then we also have evapotranspiration impacting the water surface of the lake there. Also direct precipitation. So precip and temperature is impacting all of these functions within the system that we're modeling. So if you have, let's say you're modeling a water delivery system, maybe for a mine site or something like that, you would have a similar situation where precip and temperature is impacting multiple components throughout it. So this would be a good case if you're wanting to simulate your system with uncertainty to, for example, maybe manage risk of overflows or something like that. This would be a really good application for using it. And not only that, we have a way to pretty easily defend the use of uncertainty in this model for our audience, because the uncertainty that we're imputing in this model are based on historical records. It's not just completely random out of the sky. I mean, it is out of the sky, but it is a defendable randomness in our model at this point. And these are the only points in this model that are driving uncertainty. But you could have many places where you have, other than that, where you have uncertainty. You might have coefficients that are driving runoff, for example. So, for example, in this runoff, I'm using AWBM. Again, just copied and pasted from our library. But in AWBM, we have some coefficients in here. So, for example, for base flow runoff, this is simulating runoff in the deeper soil layers. We have a coefficient here. It's a recession constant, KB. That's a constant, but that could have some uncertainty around it, right? We might not know exactly what that is. That's a difficult number to know. There is a number out there. We just don't know what it is, right? So we could apply additional uncertainties on top of what we already have in the model to make it more realistic. And anyway, what you end up with then is the ability on the downstream side to report values or outputs that are probabilistic, all being driven by our probabilistic inputs of temperature and precip. So in this case, we're looking at deliveries from the reservoir. We could look at the runoff coming into the reservoir. And these are probability time histories, but you can change this to look at things like the statistics. So this is the average over 100 possibilities of the future. This is kind of on average what it will do. We could look at maybe a percentile. What's the worst case? We could say, let's look at the 99 percentile. You can see that, okay, we're going to really be pushing our limits on the spillway. A lot of flooding going on. We could look at the opposite end. We could say, what's the 1 percentile? And you can see that, okay, we're not able to deliver water 1% of the time for irrigation, that kind of thing. Those are the kinds of answers we can then derive for our audience. So like I said, we could simulate this model for really any duration. Right now it's set up to just run for 2 years, but we could run this for as many years as we want. We don't even have it. It doesn't matter what time of the year you start the simulation. You can start at any time of the year, end at any time. None of those things matter. They don't matter anymore, because we're completely uncoupled now from our historical time series, even though the model itself is tied to it algorithmically, if that makes sense. So when we start adding up all of these things and then say, okay, let's run many realizations, what could happen here is that it will start to take longer and longer to run it. So now when I run it, you can see that it's taking quite a bit of time there to run the model. And so this would be a case where you could say, okay, now we're running Monte Carlo. It's going to take a while. Now I want to use distributed processing. So that would be a good way to speed up the model significantly, the model run. And in that case, then what you would do is you would select this option to run on network. And so to do that, you need to start up some distributed processing clients, is what they're called. And this really wasn't the point of this webinar, but I've got a little bit of time, so I was just going to show you that. So one thing we can do is you can just go down here, go to Start, Run, and then locate the GoldSim player. So that's what I've done here. This is just the path to the GoldSim player. So you just put that in, and then at the very end, put -dp client right there. And then you'll see that a client appears. And then we can just repeat that. Like that. I'm a little bit hesitant to actually run it because I noticed there was a warning message that popped up, I think because I had an unexpected high flow occurring and my model was unable to solve for the flow. And I have a feeling it was over here. Somewhere down in here, I have a here we go. So I'm just going to I'm not going to show this message. I hit the maximum number of loops. So it turns out that in this particular lake model, I am iterating to solve for orifice flow from the discharge pipe from the dam. Maybe a little bit too much complexity for what's needed. But I was just copying and pasting these components right before this call. So anyway, let's see how that goes. So now I've got these clients, these player clients. So these are like mini GoldSim players sitting over here. Now they didn't have to be the player. I could have just put mini GoldSims here as well. But the player is nice because it doesn't require taking a full license to use GoldSim. It's really just the ability to run this model using multiple instances of GoldSim. And so I put 3 up here. I could probably do 4 pretty easily on this laptop. So maybe I'll just go ahead and do that. Once you get on my laptop, now yours might be different, but on mine, if I were to do many more than that, it starts to be less efficient in doing its runs. But what this does is it allows us to run the model on multiple threads at the same time. So now what I can do is I can go here to run on network. And I've already had this from a previous run. If you open this up and you see nothing here, then you just click on add client, and then you just put in the address localhost. And now you could, in theory, you could have 100 computers on a network, right? You just need to put their address in here. But I'm just using CPUs on my own computer. So I have only 4 of them, so I'm just checking those 4. And then you can make an adjustment here to say, okay, how many realizations do I want to run on each at one time, or in sequence, actually, on each CPU. So these are decisions you have to make to kind of optimize how fast the model will run. It just depends. If each realization is very fast, then you probably want to increase this number. But if each realization takes a long time, then you would keep it low. In my case, they each run fairly quickly. I'll just change it to 2. Okay, and then we run, and then you can see, if I bring these back up, how they're each running. So this allows us to run the model quite a bit faster, obviously. So now that it's all done, all of those player clients then push all of their results over to this controller. This main model is called the distributed processing controller. So all the results came back over to here, and so now we can go in here and we can look at the results for all the runs. So these are these are all 100 results showing the water level in the pond here. But anyway, so there's a lot you can do now with this model now that it has these stochastic drivers of climate information to then better inform your model. And as you can see, it's a fairly flexible model as far as what time frames you want to simulate and how you want to simulate them. So that concludes the presentation. I hope that was useful. I will now answer any questions that you might have, but if you don't have any questions, thanks a lot for joining. I hope it was useful for you, and look forward to seeing you next month.